Thanks for watching the video, and it was great. So now moving on to the next stage of the conference, and this is my honor to introduce this person on stage. Professor David Patterson name is, I think everybody who came to the electronics engineering have read his book on computer architecture. He is a famous personality. David Patterson is the Purdy Professor of Computer Science Emeritus at the University of California, Berkeley, which he joined after graduating from UCLA in 1976. Dave's research style is to identify critical questions from the IT industry and gather interdisciplinary groups of faculties and the graduate students to answer them. The answer is typically embedded in the demonstration system, and these demonstration systems are later mirrored in commercial products. In addition to the research impact, these projects train leaders in our field. The best known projects were reduced instruction set computer, or popularly known as RISC computers, which I'm sure that all of you heard enough. Redundant array of inexpensive disk, or RAID. This is also another famous system. I think everybody is super aware of what is RAID system is. And the network of workstations, NOW or now, each of which help to lead $1 billion industries. A measure of success of projects is the list of award owned by Patterson's and his teammates are ACM AM Turing Award, which is one of the biggest award in this particular industry, and the CNC Prize, the IEEE von Neumann Medal, the IEEE Johnson Storage Award, the Sigmod Taste of Time Award, the ACM IEEE Eckhart Macquarie Award, the Katayangi Prize. He was also elected to both AAAS Society and the National Academy of Engineering, the National Academy of Science, the Silicon Valley Engineering Hall of Fame, and to be the Fellow of the Computer History Museum. The full list include about 40 awards and researches, and of course, if we start talking all those accolades, what Professor Patterson have received, I think the conference will be ended by that time. So he is a great teacher, professor, and he has helped so many students, and they are all successful in the industry. In his spare time, he co-authored 7 books, including 2 of with John Hennessy, who is a part of the president of Stanford University and with whom he shared the Turing Award. Patterson also served as a chair of Computer Science Division at UC Berkeley, chair of the Computer Research Association, and president of ACM. He is currently vice chair and the board of directors of the RISC-V Foundations. And this is another great initiative and the great drive started, which is initially spearheaded by Professor Patterson. So without further ado, I would like to give the stage and let's hear from Professor Dave Patterson that what's ahead in front of us. I apologize. There is a small glitch in the system. The Mr. Patterson is on his way, but there was because of some technical small glitch. There was we had some minor glitch in bringing him onto the stream. I apologize for that delay, Mr. That video will be online soon, so just bear with us for a few seconds. Thanks, audience. Thanks for bearing with us because there was a small technical glitch over here. Now we have overcome that glitch. We are going to start the presentation by Professor Dave Patterson. I know that all of you are eagerly waiting for this video, so we are going live now.
Hello. I'm happy to talk to you about how the importance of computer architecture affects the rate we're going to improve artificial intelligence. Artificial intelligence started in the 1950s, and the dominant way to think about it was a top-down approach. If we just wrote down all the rules, kind of if this happens, do that, and got the rule set right with the proper logic, intelligence would emerge. But within artificial intelligence, there was another group that said that's impossible. The only way we're going to learn that is from the data. You have to go bottom up from the data to create those rules. Human beings can't figure that out themselves. And within machine learning, there's another group that said the only way we can do this is supervised learning, where we try and imitate the neurons of the brain. And this is called deep neural networks. Deep neural networks have two pieces: training, where you're deriving from the data a model, and then once you have that model, you infer it or serve it. You put it to work. So training could take days, but inference could take milliseconds. And this deep neural network piece is what led to the Turing Award to Hinton, Bengio, and LeCun, who got it the year after Hennessy and I got it, and recognizing the contributions. So what we see as advances in AI is really advances in deep neural networking starting to work. So why is it starting to work? These aren't new algorithms that they invented. The algorithms have been around about 20 years. What's happened is that we needed a lot more data and a lot faster machines than when those algorithms were invented. It's easy to get more data today from the cloud and Internet of Things devices. But what about faster machines? Sadly, just as we need much faster machines, Moore's law is letting us down because Moore's law is getting to slow down. And as you can see in the graph below, this is Moore's law prediction of doubling every 2 years, and versus microprocessors that came from Intel, in terms of the transistors per chip, we're off at least a factor of 15 where we would be if Moore's law still held. And that lack of transistors per chip turns into performance, as you can see the graph on the right. In the 1980s and 90s, when Moore's law was alive and well, we were turning those transistors into faster computers, so doubling performance about every 18 months. At the time, people would throw away perfectly good working computers because they were 2 years old and much slower than your friend's computer. These days, nobody gets rid of a good computer. If my laptop, I throw it away only if the battery breaks or the display breaks or something like that, because the performance is about the same. And indeed, in benchmark measurements, it's only improving a few percent per year. So instead of doubling performance every 18 months, we double performance every 20 years. So we need faster machines. How are we going to do that without the help of Moore's law? Computer architects think the only way we can do this is domain-specific architectures, DSAs. They don't try to do everything, but just do a few things exceptionally well. What this means for computer architects is 5 decades of experience of designing general-purpose processors may not apply. So if you're a researcher, this is an exciting new times, new innovation, brand new ways to design computers. Oh boy. But however, if you're at a company trying to sell products, it's a very scary time because which thing should you build? And we need these domain-specific architectures for both the cloud and the edge. So the cloud is simply warehouse scaled computers with 50,000 servers in them at remote places. They also have storage in them, and distributed data centers around the world that are connected via the internet. That is the cloud. Warehouse computers all over the world. And the edge is the tiny computers, the often battery powered, the Internet of Things, or cell phones or laptops, cars, tennis shoes, everywhere. So that's the cloud and the edge. Let's do them in sequence, starting with the cloud. Well, Google was one of the first people to get excited about both deep neural networks and then domain-specific architectures. In 2013, they calculated that if 100 million users started doing deep neural networks 3 minutes a day on CPUs, they would have to double the size of the data center. Not only would that be very expensive, it would take forever to build twice as many data centers in the cloud. So they set an emergency project whose goal was to make a factor of 10 improvement over existing CPUs and DPUs. And they gave them very little time because this could happen any day that people want to start using deep neural networks. So that it was done in just 15 months from ideas to working hardware and software. And they exceeded the expectations, remarkably enough, in that short time. It was about a factor of 80 times better than the contemporary general purpose CPUs and about 30 times faster than the NVIDIA GPUs. And putting this in perspective, these are amazing numbers because factors of 10 in commercial products are rare. You can sell a lot of products if you're only a factor of 2 better. This is factors of 10 to 80. Why? Why was it so successful? First of all, an amazing number of arithmetic units. It has 256 by 256 arithmetic units, 64,000 multiply accumulators. Secondly, that they were doing work on 8-bit integer data rather than 32-bit floating data, so it can be more energy efficient and take less memory capacity and be faster. And because it was domain specific, it dropped a lot of the general purpose features that dominate CPUs and GPUs, like caches and branch predictors. This saves area and energy and lets the transistors get reused for domain specific hardware. Okay, TPU v1 was success. TPU v1 was for inference, which is the simpler task. So for TPU v2, they wanted to take on training. So it's a bigger task because it's more computation, it needs more memory, and the data has to be bigger than 8-bit integers. And then trying to figure out what were the good ideas that we should carry over and what had to be new. Well, first thing was, I said, it takes longer to train. It could take, on Google's production applications, if we were trying to do it one chip, it could take more than a year. So that's obviously, no one's going to wait more than a year to get their results back. So when you think about the bigger machines and more data lead to bigger breakthroughs in machine learning, that was true in 2015, just like it is today. The goal was to build a supercomputer for deep neural networks. And in retrospect, that was a great decision. Here's a result from our colleagues at OpenAI, just showing the thirst for machine learning training. So if you wanted to stay at the state of the art, they calculated going back to 2012 up through 2019, the appetite is 10x per year. Whereas Moore's law, which, when it was at full speed, was 10x every 5 years. So dramatically faster appetite for training at the very state of the art. A critical feature for a supercomputer is how the chips talk to each other. Google decided to build inside every chip what we call ICI, or inter-core interconnect. Each link in each direction has 500 gigabits per second, and there's 4 of them per chip, so that's pretty phenomenal. But it's not very expensive. It uses only 1/8 of the die to do the distributed switch and the interconnect. And the TPU v2 supercomputer scales up to 256 TPU v2 chips. So compared to the classic data center network, the links are faster. It's cheaper because there's no network interface card, and there's no switches in it. So it's cheaper, faster, and those don't form bottlenecks. And so that maybe it's 5 times faster at 1/10 the cost. So this was a big feature for our domain-specific architecture. Then the question is, the designing chip, how many cores per chip? For TPU v1, we had 1 core per chip. But GPUs can have 100 cores per chip. So where should we go? Well, the challenge is as the feature size gets smaller with more advanced semiconductor technology, the global wires that go across the chip don't scale anywhere, so the delay increases. So that's an argument for not making too big a core chip. Now we know that training can use lots of processors, so it's acceptable to use more cores. So where we went to advice is Seymour Cray, the greatest supercomputer architect of all time. And when he was asked, the way he said how many cores, he said, if you're plowing a field, what would you rather use? 2 strong oxen or 1,024 chickens? So we went with 2 strong oxen. So the TPU v2 has 2 cores per chip to prevent the longer, so it wouldn't have a slower clock cycle. And we thought it wouldn't be much easier to do 2 beefier cores per chip rather than 1,024 wimpy cores. What about the supercomputer arithmetic? The TPV1 success was this 256 by 256 8-bit integer multiply and accumulate. If we did that for 32-bit floating point, that would just be too much area and too much energy to do that on a single chip. And 16-bit floating point is much faster. Typically, it would be 8 times faster because the mantissa that you multiply is much smaller. So we experimented with doing floating point using 16-bit floating point. Now, if you can see in the format below, the IEEE standard, which was developed by Berkeley and led to my colleague Velvel Khan winning the Turing Award, 16-bit IEEE floating point has only 5 bits of exponent. So that is a very narrow range. You need to represent really small numbers when you're dealing with training on CPUs, and 5 bits of exponent doesn't support that small a number. So what they found was, if they tried to do an IEEE floating point, they ran into problems. But if they kept the exponent the same as the full precision, which is 8 bits, they didn't. But they didn't need very many bits of transition. So this brain float format has the same exponent, 8 bits, as single precision, but only 7 bits instead of 23 bits single precision, and that worked just fine. So this is a great result because it's faster, it's less die area, because the multiplier dominates. The multiplier at 7 bits is half of the die area of a 10-bit multiplier. And it's also half the energy. So it works better for software, less hardware, less energy. So brain float is a much better match to machine learning training. And in fact, as a result, everyone else has embraced it. ARM, Intel and many startups have decided to include brain float for machine learning. This is the floor plan of what the chip looks like. The dividing line in the middle shows the two cores, upper core and a lower core. The matrix multiply units, only 10% of the chip, interestingly. And as I said, the ICI links there in purple are just about 12% of the chip. Google did a second implementation of the same technology. After doing it, they thought that with a little bit more work, they could do another one that would be even better. So the TPU v3 has about 1/3 faster clock. The ICI interconnect link bandwidth is about 1/3 faster, and the memory bandwidth is about 1/3 faster. The big change is they decided they can do 2 of these multiply units per core rather than 1 per core as in TPU1. So 1/3 faster clock and twice as many cores, it's about 2.7 times peak performance. Now, to go that much faster, they burned a lot more power, and so it went from an air-cooled design that was on the prior slide. And so in the middle of the slide, you see these gray pipes connecting the 4 TPUs together, and those pipes contain liquid that cools the chips. It has more memory, twice as much memory as TPU v2, and we can scale up to a much bigger supercomputer. It goes up to 1,024 chips. The die size grew only a little bit. It was in the same technology despite these enhancements, because basically the Google designers had a better idea of how to do the layout the second time around. Before we talk about scaling, let's talk about individual chip performance. Well, we need to do benchmarks. Now for TPU v1, we use production applications to evaluate that, but that works for Google, but no one else could use Google's production applications because we keep them secrets. And so we helped create benchmarks that the whole industry use called MLPerf. We, with some other organizations, got it on the ground floor. So we've got 2 sets of evaluations of how the speed up of the TPU v3 is over the contemporary GPU, which was the Volta. So using the MLPerf benchmarks, where Google works hard to get them running and NVIDIA works hard to get them running, it was about a tie. It's about the same speed. The geometric mean is 1. Now, if we look at Google production applications, it's completely different. The TPU is 5 times faster. So how could that be? Well, what the problem was when we talked about that brain floating point format, the B float, which is in TPUs, was easy for Google application developers to use, but they couldn't and didn't want to get IEEE FP16 to work because that takes extra work to get the same results, and you have to change the software to do that. So we didn't do that. So we thought, so that was our experience, but we're not the only one who does that. The Vector Institute also is in Toronto. Only one of the 200 people used the 16-bit floating point when they use GPUs. Everybody else uses 30 points. So we'd probably get that same factors of 5 results, different there. Okay, let's talk about Scaleup. Remarkably, AlphaZero, this is the program that beat all human beings of the world at both chess and Go and one other game. It is almost perfectly scaled up. So with 1,024 TPU v3 chips, it goes 980 times faster, which is 96% of perfect speed up. And 3 other applications run at 99%. So it's just almost perfect scale up. It's just what you want from a supercomputer. How can we compare this domain-specific supercomputer to conventional supercomputers? Well, it's not going to be apples and oranges, but there's some similarities. So we're going to use the AlphaZero program, that one that beats everybody at chess. This is the production program in Go, and using it real data. And it's using BrainFloat 16 and IEEE 32-bit. That's its calculations. For supercomputers, the most common benchmark is LINPACK. This is a benchmark that isn't fantastic. You can scale up to any size in LINPACK to keep all the processors busy. This is called weak scaling, and it's synthetic data. It's not real data that is created. So the more chips you have, the more data you get. The other difference, they're not running the same benchmark, and also this is doing 32-bit and 64-bit floating point instead of 16 and 32. And so the results are at the bottom. So remarkably, running a production application, AlphaZero gets 70% of peaks. That's 70% of 1,024 chips times the peak performance per chip, which is amazing. But you can see for LinPack, the two supercomputers we have here get about 60%. In terms of the actual petaflops per second, it's almost 90 for TPU-v3 versus 60 and 1. The reason this slower computer there in yellow is there is because there's another way you can look at the LinPack results. It's called the green 500, which resorts the top 500 lists by flops per watt. And the green 500 winner is the Saturn V there at 15 watts. But TPU-v3 is 10 times better performance per watt than the #1 green supercomputer, which is pretty remarkable. Okay, that's a tour of using domain-specific architectures for the cloud. What about the edge? So here's two examples. The first one is from Alibaba, called the Gentil 910, and then a startup company also using RISC-V like the Gentil 910. But it's a very inexpensive computer intended for Internet of Things devices. So what is this RISC-V stuff? Well, if you remember from your course that, if you remember from your computer architecture course, is that when software talks to hardware, it has to talk in a vocabulary. And we call that vocabulary an instruction set or an instruction set architecture. So up until recently, all instruction sets have been proprietary. To speak to a computer, you have to get a license from somebody. The two most popular ones are owned by Intel and by ARM. So a decade ago, Berkeley asked the question, why do instruction sets have to be proprietary? Couldn't we allow an open architecture and open source IP? And we called that project RISC-V for RISC-V. And it's called RISC-V because in the 1980s, I worked on 4 RISC projects. All right, and so what is different about RISC-V? As we said right at the beginning, it's free and open. That means anyone can use it, which is going to lead to more competition and more innovation, I think. From a startup company's perspective, the benefit is you can pick the ISA first and then pick the vendor later. So that's a big benefit for them. Otherwise, you have to, if you're a startup company, you have to sign a contract, and it can take 3 or 6 months to negotiate a contract because you want to be careful about how much you pay for that, because there's usually a royalty that's associated with one of those IP licenses. It's for both the cloud and the edge, both 32-bit computers and 16-bit computers. It's designed to be easy to enhance. This is important for domain-specific accelerations to be able to add instructions to tailor it to the applications like artificial intelligence. Basically, you just need room to evolve the design when you do that, and we knew that was going to be important in the future, so we left room for evolution. Another thing that's different is that it's modular, in that there is a base core instruction set that has about 40 instructions that runs the whole software stack, and then if you want to, you can add these optional extensions. This is very different from all previous instruction sets, which require you to include any new enhancements have to be included there forever in the future. So it's kind of like as you get older, your body typically gets bigger, gaining weight over the years. That's what happens to instruction sets too. For RISC-V, there's optional extensions that you can use or leave out, but you can go away with just the skinny 40 instructions, and that works fine. That core is simple and elegant. It's very similar to the first RISC processor that we did in Berkeley, far simpler than the ARM x86, which their instruction set vocabularies are dictionaries that can be several inches wide with thousands of instructions. It's, instead of owned by a company, it's owned by the community. There's a foundation called RISC International that owns the instruction set. And so it can keep going no matter what happens to an individual company. RISC-V can keep evolving it as long as people are excited about it. Another issue that came up is security and trustworthiness in this modern world. Basically, because it's an open architecture, you can design the core yourself so you don't have to get it from Intel or from ARM. And then it enables open implementation so you can see what's inside it, just like the same benefits for, say, like Linux. You can see what's inside Linux, and it helps you feel more secure about what's in there. RISC-V International is incorporated in Switzerland, and there's, I'm surely, more than 600 members today in 50 countries all over the world. So one of the confusions about RISC-V is RISC-V an open source architecture? And the answer is no, and let me explain what the point I'm trying to make here. So there's two things. There's specifications, which are on the left, and there's designs across the top. And the designs are about source. So specifications would be like an instruction set is a specification. So example, there's three rows here. So a specification can be closed, like spec going from bottom to top. It can be licensable like ARM, or it can be free and open by RISC-V. Similarly, the designs can be free and open, licensable, or closed. So what's the interaction between the rows and the columns? Well, if you have a closed spec, your only option is closed design. Intel will stop you from getting design because they won't license it to anybody. If you have a licensable spec, like ARM, then you can do a design yourself, which they'll charge you for. You can design it yourself, but more likely you'll get the design from somebody else. So how much does that cost? About $5 million today and a 4% royalty, and $25 to $50 million to have a license to design it yourself. What happens when we get up to the free and open spec? Well, then you can do everything. You can get you can do closed designs, and this is what NVIDIA does. You can get licensable designs. Andes and Sci-Fi sell licensable designs. Or you can do open source designs, and that's what the green one. So RISC-V is a specification that is open, and the big deal enables open source designs. And examples of open source designs are Rocket from Berkeley and Pulpino from ETH Zurich. Okay, so technically RISC-V is not an open source architecture, it's an open architecture which enables open source implementations. So this IP can be a lot of money. As you can see here, about a third of the cost of a modern ASIC design is in the mask, and about a third of them is in intellectual property, as well as actually doing the work to design the chip. So my vision for this RISC-V is that it'll be everywhere, you know, in Internet of Things devices all the way up to supercomputers. But there's a secondary vision, is that by having open source, that we can collaborate across the world. Our thoroughly globalized computing industry, we might be able to release tensions. If you're working with people all over the world in open source hardware and open source software, maybe that'll make it easier for us to collaborate across the world and reduce some of the tensions that have come up. Speaking of cooperating all over the world, let me tell you about the RIOS Lab, which stands for the RISC-V International Open Source Laboratory. So our mission is to make the RISC-V ecosystem world-class. It's a nonprofit organization. We're going to judge success by a number of people using our ideas. Everything is going to be open source. The goal is to produce industrial strength intellectual property that explicitly tries to avoid patent lawsuits. Lots of people are designing processors. There's 25 or so processors available now. We're going to try and work on what's called the uncore, the other parts of the chip that are necessary but aren't as popular to design. The Shenzhen municipality gives the base funding, and we're getting matching funding from companies both in Shenzhen and all over the world, as well as money. We're getting help from them in terms of engineers to work on these open source projects. This distributed lab will have the majority of the engineers at TBSI. That stands for the Tsinghua University and UC Berkeley joint venture that has been in Shenzhen for 6 years. This lab is going to be on this campus. And we'll also teach about RISC-V. And, you know, like other graduate programs, try and create future leaders of technology. I'm the director. My former student, Zhangji Tan, is an adjunct professor and co-director, and another Berkeley alumnus, Professor Lin Zhang, is a co-director, and they'll be running the lab there in Shenzhen. To give some direction to this effort at the RIOS Lab, we want to be building hardware to make sure our intellectual property will actually work. So we've decided to target something we're calling Pico Rio. That's the logo right there. This is going to be a small board computer based on RISC-V. So you can think of it like the Raspberry Pi, but it's going to use the open RISC-V architecture and open source IP instead of the closed source ARM architecture, closed ARM architecture and closed source IP. The goal is every year we would increase the amount of sophistication and try and use more open IP each year. Eventually, after a couple of years, we'd hope to have everything open if that's going to be possible to do. And the RIOS lab is going to be the gatekeeper of this for the hardware and software. And we're going to license it to be manufactured at low cost. And this will kind of kill two birds with one stone, as the proverb goes, and that we'll both be able to use it as a device to push the intellectual property development, as well as to be able to help software developers. And few are going to pay $500 or $1,000 to be able to develop for this new RISC ISA, but if we could bring that price down to be closer to the Raspberry Pi license, we think many people would do that. So we think we'll help software development as well as test our ideas by working hardware. We think the first version is going to ship in the first half of 2002, and there's a talk you can find online by Zhangxi, but also here's the document you can find out about it. So let me conclude here this talk. Machine learning needs faster machines to advance artificial intelligence, and this is being done with machine learning and deep neural networks. With Moore's law slowing down, the only way we're going to do this is domain-specific architectures. Google's TPU-V1 demonstrated you get factors of 50 of performance per watt over general-purpose computers, which is a very exciting result. And besides, in the data center, we're going to need these domain-specific architectures on the edge as well. RISC-V is a boon to doing domain-specific architectures because it gives you a standard instruction set that you can enhance, add your secret sauce for your applications. The RIOS lab at TBSI in Shenzhen is going to develop open source IP that everyone can use to help you build these chips. And if you or organization are interested, you should contact us. RIOS is actually Spanish for rivers, and we picked that name because rivers symbolize collecting resources from many lands to create this strong force that can change the landscape. And we hope the RIOS lab at TBSI is going to collect lots of resources from all over to create a strong force that will improve the technology landscape. Thank you very much.
Thank you, Professor Patterson. This was such an amazing talk, and it's such an inspiring. We are in the industry, and still we remember those days when we studied and read your book. And I'm sure today, after this, you have inspired so many people in the audience. While your talk was going on, I got ping from across the globe, and they are super excited about your talk. And thanks for taking the time out and do it. So with that, there is a Q&A session for that. There are a lot of questions for you. So I would like to come on stage, ask some question. The first question comes from IESA organization itself, and IESA, who is hosting this conference, it is the Indian Electronics and Semiconductor Industries. I would request Dr. Satya Gupta, who is the chairman of IESA, to come on stage and ask the first question to you.
Thank you so much, Professor Patterson, for taking time this late in the night and joining us. Amazing talk. As usual, your technical acumen is very, very nice. The question which is in mind of a lot of us, that for last 30 years, three architectures have dominated basically the world of computing: x86, ARM, and RISC or MIPS, and now RISC-V, right? Now the computing taking many different directions. Do you think we are going to see hundreds of different architectures serving different needs of the computing, or is it going to be still limited to 2 or 3 leading architectures in the world?
Well, like I said in my talk, we think the future domain-specific architectures And so the benefit of RISC-V is that was designed with that in mind. Opcodes were set aside to make it easy to extend. I think it's not so much the technical details of the instruction sets as it is a completely new business model. This idea of an open architecture that all of us own, right? You can think it makes a lot of sense. Why should we have instruction sets that are proprietary? Software speaks to hardware in this vocabulary. I don't see the benefit of it being proprietary. It doesn't need to be proprietary. I think people have kind of switched around in the RISC-V community from, well, why would you use this flaky new thing, RISC-V, to like, why not? Why, if it's open and all of us can use it and we can extend it and there's not hassles, then we're just limited by our imaginations, not by some rules. So I fully expect RISC-V of the next 5 or 10 years to become the most popular instruction set. Because I don't think we need a lot of different instruction sets, but we do need to enhance them. So as RISC-V is pretty well set up, this idea that everything runs on the 40 instructions, whole giant software stack, and then you can either take pre-designed instructions to enhance it or do it yourself. I think that's going to be a pretty stable idea for the next decade or so.
Thank you, Professor. I mean, definitely in your talk, it was very good. So, Professor, our next question comes from audience is that there are a lot of MI/ML applications are there today.
A
So
lot of
which
what?
one, there are a lot of AI, ML applications are available today. Which ones you are most excited about?
I mean, I'm fortunate to be hanging out at Google in a very strong ML group. And I think the thing to capture is this is just the very beginning of this machine learning revolution. They're kind of surprised it's working so well, and they don't know how far it's going to go. The latest breakthrough that you might have read about in the paper is called GPT-3. And the difference from GPT-2 and GPT-3 is simply it's a lot bigger. So the number I talked about weights, this has maybe 10 times as many weights. And they had thought that when they increased the weights by a factor of 10, the quality would be much better, and they were right. And so now there's huge excitement in the ML community about building really big models with 100 billion parameters, and they're excited how well it works. But it's just we're at this early stage of machine learning working well, and they don't know how far it's going to go. So I think we're going to see things bringing high quality medical care to everybody in the world, because once a computer can do it, like scanning for there's a retinal scan, there's a disease that Google's done about, I think it's retinal diabetes, that blinds a lot of people because they don't have access to ophthalmologists. We can do it in the computer as well as the world's best experts, and so once we do that, we can help people all over the world. So I expect all kinds of things that are going to benefit the health of all of us, billions of people, and we're just getting started to find out where it works well and what it doesn't. And as we build faster computers and bigger models, it looks like it's going to keep getting better. So it's a very exciting time, and it's hard to know how pervasive it's going to be, but it feels like it's going to be a big deal.
Thank you, Professor. Yeah, at the end of the day, we are generating technology to solve our social problem and the life problem. And if any of these models are solving our life problem, as you mentioned, then nothing like it. So, Professor, our second question is also towards starting from the question Dr. Gupta was asking. So you are great ambassador of democratizing the instruction set architecture, and that's what you just mentioned. How are you going to manage the divergence if the system become open?
Yeah, so it's a common question, but I mean, I think it's part of the design. It'd be simpler if we could just keep buying microprocessors from Intel, and every 18 months they'd be twice as fast. That was true for decades, or a couple more, 2 decades anyways, but that's no longer true. So no matter what you do, you're going to have to add extensions for acceleration. Right now, with the proprietary models, those extensions can only come from Intel or ARM. But that's just stifling. That's just stifling innovation. I think we can just keep track of. You're allowed to have custom instructions, and there's an opcode space you can put them, and you'll run the standard software set, and then you'll have some special instructions. Maybe you can access them via a library that you do that. So I don't think it's going to be that big a deal. I think the thing to keep in mind is binary compatibility was overwhelmingly important for the PC and for smartphones because that's how we distributed software in binary. But that's a small part of the market. The most exciting part of the market is the cloud and IoT. And there's no binary compatibility requirement there. We control the software stacks in both of those places. So we can easily incorporate accelerators without screwing up all the software. And because binary compatibility isn't important as it was back in the PC era. So I don't think that would have been a big problem if it was still binary software distribution and everybody only had PCs. But that's not what the world looks like in 2020. So it's not as big a problem as it used to be.
Okay, that's a very good answer, and thanks for setting the direction. Yeah, I mean, we don't need to have a general purpose processor. I can move like you can have an Uber of application, right? I mean, I need a very tailored application. I need a processor for that, and we can get it. I think we all are excited about the new direction you have set up, and this is definitely exciting for us. Thank you.
Yeah,
Thanks for your insight.
I said the way to think about it is you need a standard instruction set to run user interfaces and stuff like that. But given how pervasive machine learning is, we have to run kind of standard software and then plus accelerators. And the secret sauce is in the accelerator, and most of the computation is there. But you don't need, a RISC instruction set works great for the user interface stuff. And then we'll use the extensions to make the AI part, which may be where the secret sauce is of the applications in the future. And I think that'll fit really nicely in with RISC-V. That division of responsibilities is going to work well with these kind of architectures, and it's a very exciting time. You're fortunate if your students getting into the field now. Boy, what a fun time with the revolution of machine learning and open architectures, letting everybody innovate in hardware and software. What a great time to be coming into the computing field.
Absolutely, and thanks for setting up the direction through the foundations and all, and definitely, and we can see that there is a lot of excitement in our academia going through that path. So thanks a lot for your time. I know it is quite late. I will not hold you back, and thanks for taking time out so late in the night and deliver this talk. And thanks a lot for your time and presentation. So let's give a big round of applause to Professor Dave Patterson for his exciting.
Good luck with the rest of the conference. Bye.
Thank you. Thank you.